Okay, this is the homework assignment about time series. So here's a picture of time series, and you can see this red is kind of jumping up and down. But the thing about time series is that the x-axis is time. So it can be days, it can be months, it can be years, it can be seconds, minutes, or whatever. So you might have, this could be a stock price over time, or it could be electricity consumption over time, or anything that's measured over time. So one difference between time series and other data is, suppose we say that there's like a trend line like this blue, kind of like a regression line or a regression or some kind of trend anyway. So you can see, if we look at this, let's see if we can blow it up. Yeah. So you can see that, for example, here, if the value is above the trend line here, then probably the next moment it will also be above the trend line. And if it's below the trend line, then probably the next moment it will be below the trend line again. So that's a property generally of time series. Now, when we do certain kinds of analysis with regression, we usually make an assumption. For example, we do things like what are called confidence intervals and t-tests and so on with regression. We didn't get into that, but that's common in regression. And when you do those kinds of estimations, you make part of the assumption in the estimation process is that that the error off of the timeline is random. It's not random here, because if it's high here, then it's going to be high in the next moment as well. Now, of course, it's not completely true, but generally speaking, that's true. So it's not random. Random would mean like you might have high here, but the next moment you would have low. You might have low here, but the next moment you would have high. That's not the case here. So it's not random, not what we call random. And we say that there's a correlation between the error in one moment and the next. So that's called, in statistics, that's called autocorrelation. So we would expect that time series will have this autocorrelation, but that's not generally a good idea when you're doing regression. So that's one issue having to do with time series. So with that in mind, the first question says, how is a time series different from non-time series data? So that's the main difference. And also, of course, that the x-axis has to be time in order for it to be called time series. Okay, typically time series have only two attributes. So what about the airline passenger data? So that's what he uses in the video, and I have it here. And we can see that there's the date and there's the passenger number. So if this is the time series, and it is, there has to be a time variable, and there is the date. So in terms of the input variable and the output variable, the input is the date. The x-axis is the date, and passenger number is the y, or the output. So we'd be trying to predict how many passengers we're going to have based on the date. So next question is passenger number numeric or categorical? Of course, it's numeric, and you can see that it's numeric here. You can also just look at the data. You can see that it's numeric. Now the other thing is about the date variable, and if we save it as a CSV file and take a look at it. So if we look at it in in Excel, it looks like a date, like we would expect a date to look. I'm not sure if this is the right date, but it does seem to be right, actually, maybe. And in fact, it's also in the R file, it also looks like a date. And it's even denoted as date type, just like passenger number is denoted as numeric, and this date is denoted as a date type. And then in ARF, you also give the format that it's in. But for some reason, I don't know exactly why this is. It's in, when we look at it in Weka, it's this kind of strange, oh, it's okay. Okay, so but actually, if we look at it here, if I click on it here, and I see that it's these weird numbers. So somehow these are, this is the way that Weka is reading it. So it's not really understanding it as a date within Weka. So these are, I think these are the number of seconds from a certain date. I forget what date it is, but like 1970. So we can see, I think it might be 1970, like it might be January 1st, 1970. So we saw, when we looked at it here, that here it's we can see the first one, the date is not 1970, it's before 1970. And so that's why this is a negative number. Okay, it's before 1970, and so it's a negative number. And the maximum actually is also before 1970. So is that true? Let's see. Yeah, the maximum is also before 1970, so that's also a negative number. So Weka is understanding these as numbers, as a data type. It does say date, but still it's interpreting it as a number. So I'm not quite sure about how Weka is handling this, but we can see that it's thinking of it as a number. And this is the number of, not seconds, it's actually the number of milliseconds measured from 1970. Okay, anyway, going back to question 4, is it numeric or categorical? Passenger number is numeric. You can see that here. Almost every time in our previous study, the class variable or output variable was categorical. So most of the data we've had so far has been, the output has been categorical. When the data is categorical, we use a confusion matrix. Think about and explain why it doesn't make sense to use a confusion matrix for a numeric output variable. So, if we have a categorical variable, for example, it might be play or not play, so then we can make a confusion matrix like this. No and yes, I guess means play and don't play, and no and yes again. And then I forget, actually in Weka, I think the top one here is predicted, and this is the actual. But I think in most times you'll see this in the literature or on the internet, it's the reverse. So this is the predicted, and this is the actual. But anyway, whatever it is, this might be the predicted, this might be the actual. This is the confusion matrix. And we only have a few entries. We only have 4 entries here because we have 2 by 2. And the reason we have 2 by 2 is because the categorical variable has only 2 possible values. But if you have a numeric variable, not categorical, numeric means basically like a real number, then how many different possible values are you going to have? Well, you're going to have an infinite number of different possible values. So you can't have an infinitely large confusion matrix. This is infinite and this is infinite. We can't do that. And so that's why we can't it doesn't make any sense to have a confusion matrix in that case. So in that case, we use some other kind of measure of the error, not a confusion matrix. And for example, the accuracy, the number of times that we got the classification correct. We don't do that when we have a numeric output variable. So there are several different variations of the measure of the error that we could use, but the basic idea is, for example, the root mean squared error, the root mean squared deviation. You can use the word deviation here or error. RMSE, root mean squared error, or RMSD. Basically, it's just this formula here. So T is just the number of instances that you're working with. So in the Weka data, we have 144 instances, so T would be 144. And all we're doing is we're taking the predicted, for each instance, what we predict, or let's use this notation here. For each instance, what we predict is usually written with a hat on the top. So Y hat would be the prediction versus the actual value. So we just take that difference, that's the error. And that's the error for that particular instance. And we just sum up those errors over all of the instances. And then we divide by T. Now, you'll see the square here, which doesn't look like we are summing up all the errors. It looks like we're summing up the squares of all the errors. And the reason we do that is because if we summed up all the errors, sometimes the error, as we saw earlier, is going to be above the trend line or above the prediction, and sometimes it's going to be below the prediction. So we're going to get negatives and positives, and we don't really want that cancellation that would occur when we sum that up. We don't want that. So we have basically two choices. We can either square the error, that gets rid of the negative sign, or we can take the absolute value. And mathematically, it's much easier, believe it or not, to square things rather than work with absolute values. Absolute values are pretty hard to work with. So we square, and then that's why we have the square root here, because we did square. So we want to take the square root at the end to bring things back down to some kind of normal size. And that's called the root mean squared deviation, or the root mean squared error. So that's a typical way. And if you wanted to do, instead of the root mean square, if you wanted to use absolute value, then you wouldn't need the root. You just have the mean absolute deviation. That would be MAD. So you could do it that way, or you could do it with the root mean squared deviation. Anyway, so going back to our question, it doesn't make sense to have a confusion matrix. So around minute 1.5, what measure of error does he? So here you can see his Weka output, and he says he's going to be focusing on the root mean squared error. So there are other measures. Here's the relative absolute error. I think that's what we meant by MAD. Oh no, that's right, mean absolute error. I'm not quite sure what this one is. Relative probably means that it's divided by something. But anyway, you can look them up. They're all basically the same idea. So we're not going to be using the mean absolute error, or the MAD or the MAE. He's going to be working with this one, the root mean squared error, the one we just showed. Okay, here they say using the visualizer, show a screenshot of the passenger number versus the predicted passenger number. We don't have a predicted passenger number yet, so we have to do a classification and get a predicted passenger number, and we have to do a little bit in order to get a variable called that as well. So let's begin by running a regression, which is under functions. And here you have to remind Weka that you want the passenger number as the output, and you can get that. Okay, so actually no, we can just get it just by going here. We can look at this. So we just go to visualize the classifier errors. It already has in it, because we ran the model, it's already available to us. There's something that's been created called the predicted passenger numbers. So of course that's different than the passenger numbers themselves, right? The passenger numbers are the actual passenger numbers for a given date, but we have now a linear regression which will predict the passenger numbers, so we can compare them. So I think we might expect that as the passenger numbers increase, as the x-axis increases, the passenger numbers increase, we would hope that the predicted passenger numbers would also increase. And that does happen. You can see that as you move in this direction, the points move up. We also don't expect it to be perfect. That is, when we move in this direction, we get exactly a line here. There might be, that is, we don't expect there to be a one-to-one correspondence between them. Okay, now we can also do the date, which is asked for in the problem. And now we have, as the date increases, and here we see these weird numbers again, because they're in milliseconds from 1970, I believe. So anyway, but nevertheless, as we move in this direction, the predictions go up linearly. Now these are linear because the model is linear, so we expect that it should be linear. Now it doesn't, I'm not sure about, it should be linear. So that's the picture. Okay, going on to the next question. What's the minimum value for the date variable and what does it mean? We just talked about that. So if we look at the date, you can see the minimum is this, and it means the number of milliseconds from some given date, which I believe is 1970, January 1st. Okay, now you saw in the video that he converts the date variable to months. So it's not in months, it's in seconds. So we'd like it to be, at this minimum value, we'd like it to be month 1. And then the next instance in our data set, we'd like it to be month 2. And the next instance in our data set, we'd like it to be month 3. So we want the date value to be 1, 2, 3, 4, and so on, until we get to the last instance, which should be probably like 144. Now I forget whether his formula starts at 0 or starts at 1. But I guess maybe the first month is called the 0th month. I forget which one he does. And okay, so what is the name of the filter that he uses? So he starts out by using the add expression filter. Now we had, you were supposed to possibly use this when you're creating derived variables. So he uses that here, and if we click on it, we can see what it looks like. So what we're supposed to do is put in some expression here and give it a name here. So I believe the name he does is new date. And then the expression is based on this variable here, which I think we refer to as A2 here. Maybe they tell us that here. So the name, the expression, yeah, supposed to refer to the attributes, I guess, with this kind of notation. So we want to refer to this one as A2, and we want to do some kind of transformation. In other words, we're kind of making a derived variable. We want to do some kind of transformation on A2. Okay, so next question is, he shows the model for new date versus passenger number, and the model turns out to be this in his video. So I guess he starts at 0, because the question says it started at 0. So the question says, if new date is 0 in this model, what is the prediction? So we can see that if you put in new date equals to 0, this term will be 0, and the prediction will be 90.44. Okay, so that's the prediction based on this linear model that he got. And you can see it here. Passenger number equals, actually, why is it 0? I think he changed something. So here's the model. And so it's this times new date plus this. So if this is 0, this is the prediction. So this is the first instance. So this would be the 0 value after we convert everything to months. So this would be the 0th month, I guess. And so the actual passenger number was 112. So our prediction is a little bit less than that. Our prediction is 90 or 90.44. So so that's what our model predicts. Note that new data equals 0 is the first element of our data set. How many passengers are there actually? So I think we just saw there were 112. So what's the error? So it's 112 minus the 90. Just make sure I got that right. 112, yeah. Okay. So that's the error between what the model predicts versus the actual number for the first element. And so there is some error. And like we said, we expect that there's some error. So we have the regression line, and then we have the dots. So the regression line represents the prediction, but then we have the actual value, which is not necessarily on the regression line. It's a dot that falls off of the regression line. So there's some error there. And for the first instance and our given model, the error was 112 minus 90, approximately. Okay, the next thing is, it says at minute 5:09. So here we see that the data is, he says that the data is cyclic. And we can see that. So you can see that like there's a peak here, then it goes down, and comes back up a little bit, goes down a little bit, goes back up to here, down a little bit, up, and it goes up to here, then it goes up to peak, and then it does basically the same thing over and over again. But the whole pattern is increasing, but there is this cyclical part of the pattern. So that's what he means by cyclic. And on the other hand, our regression is just a straight line, so it's not capturing that. In other words, we're predicting just this red line. It would be much better if somehow we could have a regression equation. I wouldn't call it a line, but that it goes up and then down and up and down. We still don't expect it to be perfectly on these dots, but we would like to get some kind of regression curve that captures that kind of cyclical nature of the data. Anyway, the question says generally how many dots are there between one peak and another. So let's say here's a peak, and then here's maybe another peak. How many dots are there? Let's say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I guess there's 12. So that means what? That this cycle is a yearly cycle. So it gets to a peak, goes through 12 months, and gets to the next peak. Goes through 12 months, and gets to the next peak. So you can really see that there's some yearly pattern that's going on, or we could call it seasonal pattern. So the question is, how could we get a regression that will pick that up? So somebody thought of a very clever idea, and that is, instead of using time as the input variable, we're going to do a lag of passenger numbers and use that as the input variable. So we're going to do a regression based on lagging the passenger number by 12 months. And we talked about that, and he talked about that. So we're going to do a new regression. We're not really going to include time, or we might include time, but I think it throws out the time variable as not being very useful. And anyway, the main input is going to be the passenger number 12 months previous. So, and we're going to expect a very strong relationship between what happens 12 months ago and what happens now. As we see, when it peaks here, it's also going to peak in 12 months. When it drops down here, it's also going to drop down. So there's going to be a very strong relationship between what happens to this one variable, which is 12 months lagged, and now. And so we expect that the regression will be very good because there's a strong correlation between these two variables. Then once we do this regression and we get the new prediction, it's going to be very close, much closer to the actual predicted numbers. That means it's going to look something like this, going to move up and down. That is, our prediction is going to move up and down and so on. That's going to be our prediction. Then we can graph that prediction versus the time, go back and use the time variable for the graph. So we have the time variable, but we're going to have the prediction based on this new technique that we're doing, which is going to cause our predictions to go up and down. Going to be very close. If we fit it to the data, if we put it on top of the data, it's going to match the data much more closely than this red line will. So one question is, you might ask, well, is it fair to use last year's data to predict the behavior of this year? Sure, it's fine. There's no problem. And what I mean by that is we have so if I want to predict what's going to happen today, I have last year's data. There's no reason why I can't use it to predict what's going to happen today. What I mean by that is if I want to predict what's going to happen today, suppose this is today, I can't use data from the future. I mean, I do have data from the future in this picture, but if I want to use this practically and I want to actually predict what's going to happen tomorrow, I don't have future data to do that with, but I do have past data, so I can use it in the prediction process. Okay, so anyway, the question is, what two filters does he use to create the lagged variable? So we want to create the lagged variable before we can use it in the regression prediction process. We have to first create it. So how does he create it? So he says he's going to copy. First, you have to copy the passenger number variable. So let's do that. So we have this copy filter, and we want to copy attribute number 1. I think you can just use a 1 here. Let's try it. Yeah, so we get a copy of the passenger number. So if we look at this now, we see that we have passenger number and a copy of the passenger number. And then the next filter he uses is this time series translate. So this is, I guess, designed for time series, and translate means to push it ahead or push it back. So let me look at this in Excel just to show you a visualization of this. So here we have the original data, and let's just make it he just made a copy, so let's make another copy. Let's make a copy here. Let's put it here. Okay, so all he's doing with this time series, whatever it was called, time series translate anyway, all he's doing is taking this, let me just select the whole thing, and he's just dragging it down, but that's all he's doing. So he's doing this, dragging it down to, I think it was at 1, I think we'd have to put it here. Is that right? I think so. Let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, so we put it here. Now, again, what are we doing? We're going to use this copy. I guess we should rename it copy. We're going to use that to predict this. We're not even actually going, I don't think we're even going to use the data anymore. We're just going to use this. So it's like we could delete this maybe. So we're going to use this to predict this, and this to predict this, and this to predict this, and so on. And we're going to look for a linear model between this and this. So if you wanted to do this in Excel, and I think we've done some regression like this in Excel before, let me just delete this just to make this a little bit simpler. And then you can, later on in the video, you can see that we need to do something about what's going on here. This is missing. So we could just, what he does is he just deletes this, but he does it in Weka. So you get that. Okay, let's try to do this in Excel. So you use data analysis, and you use, I think it's regression. And the Y input is here. So let's just select that. Okay. And the X input, so as we said, we're using this to predict this. So this is the X variable. We only want to go down to here. And we have to say that we have labels in our data set, because we do. The top row is labels, so we have to tell Excel that. And we want to see the line fit plot. So we want to see a picture of this. So let's see that. So we're doing that. And there is this regression, but this is a little bit misleading, because this is not the time axis anymore. Okay, it looks like that. But this is not the time axis. This is the previous 12 months lagged. I guess I should have renamed this 12 months lagged passenger numbers versus the passenger numbers. And here we get a pretty good model. Maybe it doesn't look that good, but anyway, it is pretty good. Then what we're going to do is take this. This is actually a relationship between this variable and this variable. So we're going to take that, and we're going to get predictions for each date. We're going to get a prediction, and that is going to be the predicted variable. Okay, so it says, what two filters does he use to create the lag variable? He uses the two that we just mentioned. We didn't actually do this one yet. So it's this filter here, which is in the unsupervised attribute, and we have to tell it which attribute we want to translate or we want to shift. And in this case, we want to shift 1. Is it called A1 or 1? I guess it's called 1. And we want to shift it back 12. We try that. And now, I think you have to change something here first. I think it didn't work. Or did it work? Oh, actually I wanted to change the other one. So let me undo that. Click here. I want to change variable 3. And I think he said you have to change this. It won't work on the class variable. So let's change the class variable to something else and try it and check it. Yeah, now I forgot to undo it. Didn't seem to undo it. Let me try and undo. And undo again maybe. Let's see what happens at it. Okay, now we're back to normal. Okay, let me try it again. Yeah. Now let's look at it. Okay, I forgot. I have to do this. Change this to here. Apply it. Okay, now you can see that it's been shifted down. Then we just have to delete these instances because it won't make a good model otherwise. So those are the two filters that he uses. Then it says at minute 6:55. So at minute 6:55, there's only one input variable, and the output variable is passenger numbers. Okay, actually, I think I made a mistake in this question. I meant to ask you at about this time, how many input variables are there? So at this time, this is minute 7, so this is after he's now used the new variable, the copy of passenger numbers lagged by 12. So now we have new date and this. So he didn't actually delete this, so it's actually included. But we have this new variable included in the prediction of passenger numbers. So this should have said at minute 7, but okay, we'll leave it like it is. So one thing is you should note that this is still what we call linear, and that is the explanation that I go through here. So there's two input variables, but there's no square on this input variable, and there's no square on this input variable, so we still call it linear. Now there are other things that it could be that would make it nonlinear, but anyway, if it looks like this, it's linear, and this looks like this. So we call that linear, even though there are two input variables. And technically, it's not going to be a line. It's going to be a plane, actually. But anyway, it's still called linear. Okay, anyway, at minute 7, maybe I did mean to ask that here at minute 6:55. But anyway, at minute 7, what is the linear model he gets? So this is it. So we already discussed this, that there's a missing data here. So we'll go on to the next question. Okay, next question is, suppose he wanted to use data from 2 years back to predict this year's data. He uses 1 year back, but suppose he wanted to use 2 years back, outline the steps you would take. So we'll let you do that. What's the purpose of the remove range filter? That's what he uses to delete this. Delete this stuff. Okay, here we can see the new model after he's cleaned up and deleted the missing values. And we can see that what happens is he didn't delete the date variable as we did, but Weka does it. It has some kind of attribute selection, and it deletes the date variable. So what we get here is we're predicting passenger numbers, but we're predicting it using our copy of passenger numbers lagged by 12 months. The date gets entirely deleted. And this is the new model. So it says that there's we take the previous 12 months lagged number of passengers, multiplied by 1.07. So it increases just a little bit from the previous year. And then we have this constant factor here. That's the y-intercept in the graph. But basically, this is the model. Okay, so what he does finally is he goes about here. Here we're looking at new date for the x-axis and the prediction. But he says you can't really see the pattern because these marks happen to be so large. They sort of hide I don't know, maybe there's no way to change the size of these marks, and so it's pretty hard to read this. What he does next is there's a add classification filter. Basically, that allows you to create a new variable, which is the prediction from whatever model you're using. And we're using linear regression. So we're going to be able to create the prediction, and that's going to be like a new separate variable. And he calls that new variable classification, and now it's been created here. And then if you use the Visualize tab, you can look at the relationship between all the variables that you have. And he wants to focus in on, he does new date versus the classification. So this is the prediction, but remember, this is the prediction that we made not based, it's kind of weird because we are showing new date versus classification, but the classification was made from taking the model, which related passenger numbers to this. So that was the classification was the prediction based on this of what the passenger numbers should be, not based on the date. But what he's showing us is the prediction, but pictured as related to the date. So here, it's a little hard to see, but there is this is the prediction. Look how the prediction goes up and down and up and down. This is not the actual data. The y-axis is the classification. So it's the prediction. It's not the actual data anymore. We don't see the actual data in here at all. This is the prediction only. But you can see it. Look, the prediction is going up and down and up and down. And that matches the actual data. We don't see it here, but that matches the actual data very nicely, or much more nicely than the linear model did. But anyway, this is the prediction. But the prediction where we did not based on date, but based on the lagged variable making a prediction about what the number of passengers will actually be. A little bit confusing, but we do get now this kind of very cyclical prediction. Okay, question 20. Repeat all the steps that the author performed to obtain the output at minute 8:25, but instead of lagging the number of passengers by 12 months, try it for 24 months. And then you might go ahead and try to make a new variable called classification in that case as well. And then you might try and visualize that and see, you'll probably also get the cyclical relationship. But one thing that will change is that the if this variable is passenger numbers minus 24, then you would expect that the passenger numbers would increase by more than it would based on this variable. Minus 12, you're only going to get a fairly small amount of increase, which is a factor of 1.07. If you did it minus 24, that's more in the past. You would expect to predict passenger numbers that this would be bigger. Maybe it might be 1.14 instead of 1.07. Anyway, try to do that. And what is the root mean squared error, and how does it compare to what he did? And also, what is the model that you get? So what does this model look like? So this is a nicer picture than the one that we just saw. But here and in here, you can see that the predictions are not the red line anymore, but this blue line. So the predictions now capture a lot of the cyclical nature of the data. And the error should go therefore way down, because the error is a measure of how far the dots are from the model. So if the model is the red line, the error is going to be much bigger than if the model is this blue curve. Now the interesting thing is, as I said, that we use linear regression, but we don't get a linear. So you should think about why that is. I've explained it here in this video, but if you didn't catch it, you should clarify it in your mind. Why is it that even though we use linear regression, we're not getting linear here? But anyway, so the error, though, is much smaller. So we would expect that the root mean squared error would be significantly smaller. Here it is a lot smaller. And then the question is, what's the input variable for the red line model? And that was date. And as I said, a little bit confusing, but what's the input variable for the blue curve model? It wasn't date. It was this one here. Copy of input passenger numbers lagged by 12. Okay, which models would have least error? We just said that the blue model is going to have a lot less error than the red model. Okay, so next questions begin with the time series forecasting package. So in this video, he shows us that all of this stuff that we kind of did manually, the package, the time series package, will do it for us. So we don't have to do the lagging, and it has a lot more features as well. So in this video, in the next video, they're going to discuss the forecast tab, and he suggests that we reload the data, or actually close this. Try closing this and reopening the data. Okay, so I reopen the data, go to the forecast tab, and if we just click start, the question is, what happens? So this happens. We don't see any evaluation. He says you have to ask it for evaluations to get them. But we do create many new variables. So we started out with only 2 attributes, but the derived variables, or the transformed training data, has passenger numbers, month, quarter. So these are created. Date has been remapped. Lag, passengers 1 month, 2 months. Presumably these are months, but we're not actually sure, but looks like they are months. Date squared, date cubed. Then it does some other derived variables. Date times lag 1, date times lag 2, and so on. These are all derived variables that it creates. Then the regression model is here. So maybe it doesn't use, say, date remapped or date times lag 4. Let's see if it does. It does. It uses that, and it ascribes this much weight to it. So you can think of these coefficients as kind of the weights that it ascribes to these different derived variables. So I'm not sure what it leaves out, if anything. Maybe it doesn't leave anything out. But anyway, well, here, these are month variables. So I explained in the homework that, for example, if you take this one here, this is a variable which is, so all of these are what we call Boolean variables. Boolean variable means that they can't, they're not like normal numeric variables. They can't equal any number. They can only equal 2 numbers, either 0 or 1. That's a Boolean variable. So this strange looking thing here, it says month equals aug_com. This is like a weird name for but it's just a Boolean variable. This can only be, this is just the name of it here. But anyway, it can only be 0 or 1. The question is, when is it 0 and when is it 1? And the name gives you a clue. So if the month happens to be August or July, then this is 1. Otherwise, it's 0. So when it is August or July, it's 1 times this, so we get an additional, we can say like an additional number of passengers, an additional 24 passengers when the month is either August or July. Now we might actually get more than that because August and July also occurs here, but it also occurs here, and here it's negative. So you have to sort of add up all the effects to figure out what the actual effect is when it's, say, August or when it's, say, July. Anyway, this is the model that we get. So going back to the question, how many variables were created? So you have to count all of these to say, so here's 1, 2, 3, 4, 5. You have to count them all. This is not a variable. This is just the constant. And how many variables that have lag in their name? So we have all of these, but even we could say these are also have lag in their name. This is, I guess we could call this the name, and so it does have lag in its name. So the model looks like this. It's a so-called linear regression model that has many variables. It looks like that. So here we say, well, we can just suppose we had a much simpler model, and the explanation of this variable, as we just mentioned, is that if the month is any one of these months, then this part becomes 1, so it's 1 times this. That means the passenger numbers will jump up by about 37. Okay, next is we want to evaluate the model on the test set by setting the evaluate on held out training. So we need to have a test set. We're going to have 25%, and we want to know what the root mean squared error is. So that is done, I believe, here, and evaluation. And then we say on the training, on the testing set, so we're going to evaluate on held out training. We're going to hold out some of the training for testing, in other words, and we want 25%, so we'll do 0.25. And if you want to know what the training was, the evaluation was on the training as well, you could select that and do start. We get that on the test set, the error, the root mean squared error was 60, so not so great. And but on the other hand, on the training, it was very low, but we're not really interested in that. Okay, next it says try a different base learner. And I mentioned here that I've never seen the ability to use other base learners in time series. Maybe it exists, but I haven't seen it. So try using a multi-layer perceptron, and let's see what the RMSE is then. So we go to advanced configuration and base learner, and we use a different one. So we use, we go here, and we go to multi-layer perceptron as the base learner. So let's click start. Okay, it took a little bit longer, I think. Anyway, here, I think this did a little bit worse than before. Or sorry, no, it's 8. What was it before? It was 7. Yeah, it did a little bit worse. And here, though, it looks like it did a little bit better, right? Yeah, before it was 60. Now, it's considerably better. Okay, the next question is, how do we remove the leading instances that have unknown lag values without using a filter? I think that is in the lag creation button, and we click more options, remove leading instances. So we can do it this way, whereas before we had to use a filter. Include powers of time, we'll leave it like it is. Include that. Okay, and I guess if we run it again. So does it get any better? What was it before for the test data? It was 25. No, it gets worse. How about on the, here was 5.6. So that got a little better, but that's not too important. Okay, anyway, that's how you do that. Okay, next question is, when there is a big difference between how well the model does on the training versus the testing, what does he attribute this problem? To what does he attribute this problem? And he calls it overfitting, right? So if we do very well on the training data but not well on the test data, means that the model is working very well on the training data, means it's overfit to the training and doesn't work that well on the test. Okay, here, how do we change the settings to create only a lag of 12 instead of all of the months? So I think that was up here in lag creation. Use custom lag length, and just minimum is 12, maximum is also 12. Let's try that. See what happens. Okay, now we go back up. We get quite a large error here, and not too bad here, but quite large here. So it looks like it was good to have created a lot of the lag variables, not just the 12th lag. Now, I'm not quite sure what the interpretation of that is. Like, what does that mean? So what happens exactly 1 year ago is not the only factor. Also what happens 11 months ago and 10 months ago, and so on. Okay, the last question about this video is, which model seems to do better on the test data, the blue model or the red model? So we can see that the blue model here is doing better. He says that what happens here is, it's called a one step ahead. So we make a prediction, I guess, here. Maybe the first prediction is here, which doesn't look too bad. But then I guess the next prediction is here, which is pretty far off from the actual data. And then what happens is, because we make a prediction from here to the next time, and so we've sort of already made a big error, so our prediction for the next step will be propagated to future times. So as soon as you make when you're using this one step ahead, and honestly I don't recall the alternative to one step ahead, but anyway, when you're using this one step ahead, the errors, if you have an error, it's going to propagate. So you're going to continue with that kind of error into the future. Anyway, which model does better? The blue model is working better than the red one. So he says that at this point in the video, we have the simple model is the blue one, and the full model is the red one. So I think earlier in the video, he took out a lot of the variables, and that created a simple model, and that is actually working better than the full model. Okay, the next set of questions has to do with the next video called Looking at Forecasts. So this is how you can visualize the forecasts using the time series package here, the forecast package. And we only have a few questions here. In the following graph, there are square and round dots. How many round dots are there? Note that the round dots are the forecasts into the future. So when Weka makes these graphs, it uses square and round dots, and it uses the round dots for the predicted values, and you can see there's only one. So there's only one forecast in the future in this visualization. So if we run this, and then we look at the graph here, we get that picture, and there's one prediction into the future, but you can change it to 6, like this, and do it again. And now you'll see there are 6 circles, or round dots, and these are the 6 predictions into the future. You can see that, and you can see that it has captured this kind of pattern here. So using the airline data, predict 6 months into the future. We just saw how to do that. Now, one thing we should do, I don't think we did this yet, we want to go and get rid of, maybe we did that already. Okay, we got rid of the leading instances, so we've done that. Okay, now if we go to evaluation, and we evaluate on the training and on the, and also we're going to hold out 6 months for testing, and we run that. Okay, so we get the evaluation on the training and evaluation on the test data. And if we look at the graph now, these again are the predictions, and they're not necessarily the same as the actual data. We held out some of the data, and so these are not necessarily the same as the data. And then here, so here you can see this pattern like this. That is this pattern here. Okay, and then but remember, this was held out. So we can do predictions even past there, because we do have the actual data up until this point. These are predictions, but we have the actual values up until this point also. So, it sounds so confusing, but so we have all this data. These are the predictions on the held out, but we do actually have the actual values up to here. So we can make predictions off into the future here as well, and that's what this shows. Okay, so what's the difference between the red and the blue here? So the red is the actual numbers. This is when he was holding out 24 instances for prediction. So, but we do have those values, so we do know what actually happened. We're just holding them out for testing. So we know what actually happened. And then we have our predictions. So that's the blue. So let's just make this clear once more, or try to make it clear. And that is, when we do hold out, we're holding out, say, the last 24 instances in his video. He's holding out the last 24 instances for evaluation purposes. But we do have those 24 instances. He's just holding them out. So this is what they actually look like, the red. But we also are making predictions, and that's the blue. And that's how we can measure the error. So the predictions compared to what actually happened. Okay, so you should be able to do this based on what I just said. And that is all that we're going to do with the time series package.